So welcome everybody to this tutorial on multidimensional process analysis. My name is Dirk Farland. I've been doing BPM research for, I don't know, 14, 15 years now. Yeah, 14 years it is. 2008 was my first conference. And I've been pondering a lot over these 10 years how to deal with processes that are not just a simple single insurance claim that you handle from start to end, right? So all the problems that are always mentioned in the keynotes, right? So how to deal with them. And it took quite a while, but especially the last 4 or 5 years, quite a few results have emerged. And it was time to summarize this. So this is what I want to do today in this tutorial. I think I'm going to fill the 2 hours. So, but I'll also involve you. I'll ask you questions. So I'll try to be easy on you. And if I see you dozing off, I'll stop. So I'll start simple, and towards the end is the more advanced things. So let me start simple. We want to study, improve processes in the real world, as Jan just mentioned in the comment to Jan Menling's keynote. So these processes in the real world, we design all kinds of systems, right? BPM systems, information systems, decision support systems, AI systems, whatever it is. It's very rich. They're there to support these processes, but sometimes also the processes support these systems. What matters for us is through these systems, when we can record data, and we can analyze this data to obtain models or kind of compare the models that we have with the data. And these models are there to describe the processes, but also to improve them. This is a picture that Wil van der Waals has been creating, I don't know, 15 years ago, and it's still valid. So let's have a look at this process. What is a process? Processes happen in the real world. For example, in logistics, when we let machines move around items. That's not the first kind of process you think of, but they're happening. We have processes where people work in organizations. They're actors, so they do things according to what the company is doing, but also on their own. We mostly use documents to manage the information flow. These documents tell us what to do, and we create these documents to tell other people what to do. We also have all kinds of procedures and rules in place to manage how people do the work in a way that we have the outcomes that we want to have, right? Healthcare is a prime example. You can't just do anything. You need to follow particular guidelines. So all these things are there, and they're complex, and they're brought in by different people, right? It's not just a single person who's doing that. And we have different, stakeholders in that sense, right? Actors work in the organization, managers, customers, people who are affected by it. And they all have their own goals. They have their own way of doing things or what's possible. And you have to agree on this in the real world. That's why we have these models. We're creating these models to describe or even prescribe how to work as an actionable means of communication, right? So these models, that's what process management is really good at. They're not just a statistical model that nobody understands. It's a picture you can show to different people, and they understand what's supposed to be happening. So this is crucial. The second thing that we need, and that agreeing on goals and actions relies on, is that we have data that is accurate. Not just accurate in a quantitative sense, but also in a qualitative sense. It has to reveal to us the relevant phenomena that are important. So let's compare this picture to what we are doing or have been doing over the last 20 years. We've been developing in the early stages of the BPM community process modeling languages, right? YAWL is, say, the prime example of the academic development that incorporated all kinds of patterns of how to model workflows into simple constructs. They're derived from Petri nets, but they're not exactly Petri nets. But they take this idea that you have local transitions in places because they're perfect fit for processes. And these models, they made it over into industry, into industrial standards like BPMN, that we now can just deploy in an engine, hook it into other existing systems, and we run these processes. So the research that came from Petrinets heavily influenced the industrial modeling languages and also the executions engines as they work. We even can annotate data, who's supposed to work on certain tasks. But there's one inherent assumption in all these things, in these models, in these engines. One process instance is executed in isolation. Right? We have the case, right? So process mining, we extract data regarding a single case identifier, and that's what we do. And this is what we exploit in process mining. I call this single-dimensional process thinking. And you think, okay, what other dimensions are there? To start with, at the very, very basic way, you can think of behavioral dimensions in two directions. One is how many objects you're looking at, and one is how many dynamics you're analyzing. BPMN describes very well how one case, one object is handled over time. One insurance claim, right? That's what it does really, really well. But there's so many things out there that this doesn't capture. Time is not modeled. We don't model workload or how multiple actors behave, things which are analyzed in queuing theory, operations research, organizational research, routine dynamics. You can't put it in there. It's outside the scope of BPMN. Obviously, multiple entities, multiple objects studied in social network information systems and in databases, right? Relations between objects. It's not in there. So, but all these things matter for processes. I mean, we know this, right? Everything here out there matters how a process runs. So that renders our small BPMN models like a point mass in a vacuum. In physics, right? When we model physical systems, what you learn in high school, you have a point mass in a vacuum and then have simple physical equations. It's good to start, but it doesn't reflect reality. If you want to solve real problems, you have to look at these other phenomena. So what I want to cover in this tutorial is to reach out into these other areas by simply looking at what happens if we add multiple objects. Some of you probably know this already, object-centric process mining, artifact-centric process modeling, but also what happens if you analyze multiple flows, multiple dynamics, and then, of course, what happens if you combine them together. So the goal of today is, at the basic, that you get an idea of how to think in more than one behavioral dimension, beyond BPMN. Just that you have an idea how to do this in a structured way, that there are some concepts that help you to do that. I want to show you also that actually all the processes that we're looking at are multidimensional. I mean, I've shown you this picture, but I want to show you more to convince you that it's really true, and that even the event logs that we have, the public event logs, even the ones from 2012 that Bardewijn talked about, so old, they show it. It's in there. You just have to look for it. I want to show you how. And then finally, that there are some simple concepts, also some basic tools that have been developed over the last years that you can apply and explore this data. This doesn't solve any problems yet in industry, but what I hope is that it leverages your thinking into approaching these problems in a different way, and yeah, to some extent, help me expand further into this space. So that at the end, next year, your papers that you submit no longer assume that processes are executed in isolation, but that you actually can include something of that outside in your work as well. Well, no less than that. So before we begin, I have to thank a couple of people who have been really supportive and transformative in reaching that thinking. The people who I've been discussing with on research proposals, PhD students, Vadim sitting here was very influential. But most importantly, I'm mentioning one company, Van der Lande Industries. They're building material handling systems, baggage handling systems, which are processes, but they're very, very different, and their problems are very, very different. And studying these helped me a lot in kind of changing perspective on many things. Okay, so that was the introduction, and this was the time to get everybody else into the room. So welcome, everybody. So now we start. I want to start with the part that you didn't expect. So I want to look at how can we analyze multiple flows over the same object in a way that we can actually get actionable insights. And then I want to look at the other two parts, right? Multiple objects, and then, well, this one here. So let's get started. Here's a very simple case. Who knows this data set, this model? 1, 2, 3, 4, 5. A few hands I see, right? So this is the road traffic fines management process, one of the public data sets. It's a rather simple process compared to many of the other real-life data sets. And here you see the three main flows. So if you drive too fast, you get a ticket. So it's a fine is created. And you can pay it on the spot, or, well, with a bank transfer. Or if you don't pay, then after, well, on average, about 90 days, you get a letter, the fine is sent to you. Then either you pay then, or, well, fine notification is inserted, and it's a penalty added, and maybe then you pay, but really, really much later, or things are sent for credit collection. So that's the process, right? I want to show you how to look at this differently. What we're going to do, right? When you animate, when you press this play button in a process mining tool like Disco or Slowness or Prom, you see these nice tokens flowing over the edges, and it gives you a feel for what's going on in the process. So let's follow one token, but not in an animation, but by drawing it out on a canvas. So I have the time axis on the x-axis. On the y-axis, I'm putting, here's create fine as an activity, and here's send fine. So if I have a case that was a create fine at time tc, well, sometime later, it reaches send fine. So I can draw this diagonal from this point to that point. Super simple. All I need for this is my classical event log. Case identifier, activity, time, nothing else. If I have a second case, and of course I do, then this may start earlier and finish later, for example. So if I do this for the road traffic fines data, I get this picture. Now comes the interactive part. What do you see here? What do you see in this picture? I'm going to switch to a whiteboard. I'm going to highlight and annotate what you say. Yeah, so you're talking about this one here, right? Yeah. And then there's another one over here and over here. What do you call that? That's batching. That's batching, right? You let work pile up, and then you do it in one go. We know this is an efficient way of doing repetitive work, right? You want to stick in your mental context and kind of just work down things. Now, probably here, this is not a human doing it. This is an automated system, right? This is sending letters. So you're sending letters by the bulk because it's cheaper, right? So they're accumulating, then they're sent out. So there's different reasons for doing batching. And here you see it. You don't see this on the left. You can't. Well, maybe if you run the play button and watch all the tokens, then maybe you catch it. But yeah. This one shows it to you. Well, what else do you see? There's more. Is everything batched? It's the first example. No, there are cases that are not batched. They're going straight through. Apparently, not all traffic tickets are equal in my process. Well, I don't know why, but at least now I can talk about it, right? I have a means of communication that allows me to go deeper into the process in the organization to say, okay, well, what's going on here? Does this matter to you? Do you want that? What else do you see? There's a standard delay for adding a penalty. Exactly, right? So, and it's fixed, right? So you see strict FIFO queuing here, right? So it's there in 60 days. After 60 days, the penalty is added. Now you're wondering why this is orange, right? So we use these colors to indicate in which quarter, which of the quarters of the histogram the duration is. And this is daylight savings time, 1 hour more, so it shows up. Other things you see. One that is slightly more difficult to catch. I'll help you. So here we have this batching moment. And then these cases go out. And then we have the penalty that's being added. But here work accumulates. Because of this batching moment here at the top, I get still a larger amount of cases reaching then the add penalty step at that moment in time. And you see in the step to payment, then, well, there are people who do this very fast and people who do take much longer. If this wasn't the payment which the customer is doing, but somebody else within the organization, there would be an indication that the batching here is creating a workload peak down there for other people. You don't see this in the process models on the left. We can go on, right? One of the things that is nice to see, like here at the top, this is payment behavior by customers, right? So it's very irregular. And maybe it's also interesting to study which customers interesting, offenders. The people who have to pay, right? So who is paying fast, who's paying slow. Whereas the rest of the process is really quite nice structured, right? So things are kind of in a rhythm. It's a good sign. So this is the first super basic technique for multidimensional process analysis. And if you look at different processes, you get vastly different performance spectra. Well, this is no surprise, but at the other hand, so seeing it kind of reveals a few things. So this BPI 2012 and 17, you see much more straight-through processing, quick things being done. The reason behind it is actually a bit more complicated, but these two processes come from the same organization, right? So you see these two processes are similar. Some of the things haven't changed in this process, also in terms of performance. Hospital billing, well, it looks a lot like this payment segment. We call this a segment, right? From A to B, we call this a segment. This payment segment, they all look the same, right? So lots of fast and slow overlapping. So maybe the characteristics of how getting a fine and doing the payment, these characteristics here are very similar to what's happening here. Though here, this is an organizational process, right? It's structured. So you wonder what's going on. Why is this so slow? Maybe there's too many customer steps involved or something like that. So you can analyze processes and compare processes in this way as well. It's very, very different from comparing control flow models. Then, of course, you maybe want to do machine learning on it, right? So here, I want to show you a few things where you can, well, I've shown you pictures, but let's do something with it as well as with algorithms. So one of the things we've noticed first were batches. So we can detect batches. The basic idea is that you're looking for a subset of the cases. It has to be a minimum number to be meaningful that end in a very short time window. And well, one of the definitions is they don't overtake each other, right? So FIFO, and then they end here in the small spot. Another option recently developed by a student that I supervised to kind of look at the relation between the opening and the closing interval. So then you don't have to look at so much thresholds. It's a bit more robust. And that allows you to kind of take apart the data and look at the cases that end up in the batch and the cases that are not batched. So you can categorize them now. And you can use this, for example, for prediction. Just sketch this very briefly. So one of the things that you can apply this on is analyzing how good is your predictor. So here in the black, you see this last segment of this credit collection process, where after penalty, things are sent for credit collection. In the black, you see what's actually happening. So there's two large batches, 2 batch points. And these blue and red lines is what the best remaining time predictor back then when we did the study was capable of doing. And you see this doesn't know batching. We never told it to know batching. So it wildly under and over predicts, and these are months, right? So this is not hours, this is months off in the prediction. So what you can do is, right, you identify these batches, then what's a bit more difficult than you locate in which part of the batch a case is. So you can estimate how much time it's going to be until it reaches the batching point. And if you add this into a longer feature extraction pipeline for a remaining time predictor, then what you get is that things improve. So the absolute error goes down from 230 to 177. It's not great, but well, it shows a bit. And the predictions are closer to the actual batching points. If we would have perfect knowledge of the batches, right? Here we're estimating the batches from historical data, but if we would have the perfect knowledge of the batches, this is how this would look like. So well, you can analyze, you can check, are my models doing any good? So it can help. Something else, switching context. I mentioned Van der Lande, right? They're building baggage handling systems. This is one baggage handling system, right? So you drop your luggage off at the check-in counter, and then it goes off into the bowels of the airport. And these are the bowels, right? So conveyor belts that move bags to screening machines over here, right? So that check X-ray the bags for any dangerous liquids, for example. And then move them on, right? Maybe they need to be stored before they go to the airplane because you arrive 3 hours before the airplane leaves. So it's an automated system that has to run. And this is the performance spectrum of a baggage handling system. Well, I have to say it's of a baggage handling system in a stress test, right? So we kind of pushed it to the maximum to kind of see how it behaves. So what do you see here? So this is kind of a path, typical path of bags from check-in to in the middle of the system, right? So all that come in order. Yeah, it's first in, first out. It's no surprise because it's conveyor belts, right? So it's good. It's good that it behaves this way. No, obviously, right? Because you don't have that in the business process. There, things overtake each other. Here, strict first in, first out. So, but there's more to see. Yes, this is a very long delay, right? And you can, this is how it can go, right? That's the speed how which the bags can travel over this. This is much longer. So this is bad. This means somehow the conveyor belt here stopped. And then it took quite a while until it moved on. So you would like to detect this, right? So how can you do this? Here's a simple technique, right? So again, this is performance spectrum. There's two detectors. One is if you have an increased load in a particular area, because if you're overloading your conveyor belt and you're kind of clogging things up, right? Just like traffic jam, too many cars on a road lead to a traffic jam. So just moving a time window over this, counting the number of bags in the time window. If you exceed a certain threshold, and it's difficult to set that threshold on kind of revealing what's meaningful. But you can, then you have a time window in which this is a high load period. I can label these bags in that part to be part of high load. And for these extra long delays, you can use the Z-score, right? So it's extreme deviations from the mean. They exceed a certain threshold, and you can label them as we call it a blockage. And typically in such systems, you have multiple bags caught in a blockage, not just a single one. Okay, so we can detect these, but there's more to see in here. You should look very closely. And this is your next level of multidimensional thinking. Who sees it? Okay, yeah, okay, good spotting. That is because, right, so conveyor belts also merge and divert, and here I'm just plotting out one sequence. So this is a spot where bags went a different route, and don't show this in this diagram. So definitely relevant to keep in mind, because the moment we plot as this dimension, certain things we can't see anymore, as we're becoming blind to some parts. But there's something else to see here. The delays follow the traffic jam. Right here, I have a delay here, and you see here, it's less dense, and the lines are getting longer. Also here, so there's some form of propagation going on. If you think of it, right, you have a conveyor belt, bags are moving. You stop this conveyor belt. Well, there was a conveyor belt before that was moving the bags there. These bags can't go there anymore. If you have what's called a divert, right, so you can route the bags around, things will flow fine. But if not, then this one also has to stop and on. Right? Just like a traffic jam. If you block the road, things will queue up. That's what you see here. you can also detect this. So this propagates, right? And it's not just propagating once, it's a second time, right? So there's this blockage of propagates, then behavior resumes, and then it propagates again. So this is systematic. And of course, this was important to find because this was a stress test, so it was good to detect this. But can we extract this from the data? Yes, we can. The idea is extremely simple. So, some slide is missing. All right, the idea is extremely simple. What we do is we make each pattern, we encode it as a node. So we create a new node, a high-level event node. We create a graph now, and we say, okay, this node here relates to all these observations on these, right? So we have a lower level log of all the movements of the bags, and we have a higher level event that connects to all these. And then whenever these patterns overlap in time, right? So that you see the overlap in time, but also they connect to each other because they connect on a physical segment, then we draw an edge. And we can get these paths or graphs, can enrich this with further information. So these are these kind of outlier cascades that we can detect, where you can see, so this is a blockage, this is high load, and you can, this is hard to read, right? So this is where kind of you need to start thinking differently. So you see here, there was a blockage over here, which then later on led to a high load over there because bags couldn't move through this part. Another part of the system was used, and it's outside of this part. Here's a blockage that propagates that you see. And we have additional information that's being added from sensors of the system, right? A kind of equipment reporting sensors that might indicate what's the reason why a conveyor belt, for example, stopped. So these are not process models. These are essentially, each of them is a short trace in the system, but not of a bag, of a higher level dynamic that propagates. Underneath, there's many things that are happening. Mind-boggling, but I wanted to show you what's possible. Okay, first part is done. So I've shown you how this super simple idea of mapping out how items move over consecutive steps in the process, and it's kind of just drawing it out allows you to see things that you usually don't see if you just analyze the flow of each individual item. Yeah, so intercase dependencies, and it indicates mechanisms that are not part of your model so far. Batching rules, priority rules that's to skip, these conveyor belt dynamics of blockage propagation. And it gives you an idea of what to look further for, right? What to ask in the organization, the stakeholders. But the key thing to get there is what I've written here first. Look at multiple things at once, right? So then I've shown you one way of doing this. Look how to look at multiple things at once. So now we want to look at, okay, I promised you tools and data, right? So this is implemented. We have a prompt plugin. We have a standalone tool that you can use. We also now have a Python implementation that really allows to kind of work in Jupyter notebooks with this performance spectrum. The batch detection, cascade detection, prediction is all implemented. And you can apply this on any classical event log. That's a nice thing, right? You don't need any special data. You can just start right away. Sorry, say again? Yeah. Yeah. So by default, right? So if you, for example, have a loop over here, then you would see cases going here, and then kind of the line stops and returns over there. I think Vadim at some point also tried to kind of indicate this jump back, but then it gets very clogged. So definitely one of the things to look further, right? If the dynamics are important over looping, you can also unroll, right? You refine the activity labels A1, A2, A3, then you split them out. So brings me back to the spirit of this tutorial, right? So these are ideas, and feel free to pick them up and to adjust them for their own research, right? We hope they're simple enough that you can do this. So that's the idea. Yeah. I think we'll be coming to that a bit in the next part. But I'm actually not touching it that explicitly, and I think let's come back to your question towards the end. I think it's an interesting one. It's a gap a bit in what I'm showing today. It's right. It's right. Okay, let's go to the next dimension. Multiple objects. I want to start with an example. So this is a retailer, takes in orders for items. Order 1 has items X, 2 times X, 1 times Y. And I made this example fit a bit, so it's 2 orders coming from the same customer shortly after each other, right? So it's not changing the order, it's just placing a second order also for a second item, for third item X and another item Y. So we have 2 customer orders. Well, this retailer doesn't have this on stock, so creates supplier orders and creates a supplier order for 3X and for just one item Y, right? So you already see that there's a problem. When the supplier order arrives, right? So it's received, the items are received, they're unpacked, and then we have 3 concrete items, X1, X2, X3, right? So they're, I distinguish them individually. In the warehouse, you may want to do this. Also having 2 invoices, one for order 1, one for order 2 that are created at some point in time. Then we realize, or the retailer realizes, okay, I made a mistake here. I actually need to order 2 Y, so I'm updating the supply order, which can also arise at some point in time. Also need to update the invoice. And only after I've received 1 Y, at least 1 Y and 2 X, I can start shipping order 1, because only then I have X1, X2, and Y1. So I'm putting all these items in there, and then I'm shipping them at say 3 o'clock. And then there's a rule in place that says if I have 2 open invoices from a customer, I will not send the second shipment before the invoice has been paid, right? So there's a payment block. I'm not gonna send out the invoice. So first, the customer has to clear both invoices, and then the second order is shipped. Right? It's a process, right? There's no case identifier here. You already see that, right? So it's orders have invoice, supplier orders, items, payments. Don't even try to build a classical event. I'm going to talk a bit about what goes wrong when you try this, but there's not the typical case identifier like this traffic ticket, right? This traffic ticket, I drove too fast, that's my identifier. And I kind of can relate everything to it, but I can't do this here. And to make this a bit interesting as well, of course, we have people, we have maybe an automated warehouse to support us. But to make this interesting, right, the supplier, so the retailer promises to ship everything within 6 days of placing the order. And I'm going to show you an event data in a moment where this is violated. So here's the event data. What is this? I mean, sure, I have event records, right? You know this, right? It looks like an event log, an event identifier, timestamp, activity, lots of attributes. It's not a classical event log because, as I said, there's no case identifier here. So what do we call this at the moment in the community? It's an object-centric event log. Yeah, that's what it is. So we can also call it a raw event table without unique case ID, or object-centric event log, or event table with entity types. It doesn't really matter. But the point is, you have multiple entity types that are indicated in the attributes, and you have all these identifiers that say, okay, I have an order 1 and order 2. I have supplier orders from A and B, and so on and so forth. So now the question is, are all the KPIs met? And this I can check on this object-centric event log by just looking at order 1 is placed at 1st of May, and it's shipped on 8th of May, so that's 7 days. The other one is shipped on 9th of May, so it's 8 days. So they're violated. Now, sure, I can see that, but why? Why are they not met? That's the big question. So who does not know, that's a good question. Who does not know why extracting a single event, a classical event log from this is a bad idea? Right? Because I have event data, and I can try, there's ways to do this. Who does not know why this is a bad idea? As if you, let me show you, right? So let me recap. If you try to build a sequential event log, what you have to do in this situation, you have to pick a case identifier. You have to relate it to something. Well, in this case, it would be the order. Say, okay, order, because this is where the process starts. That's my case identifier. Then you add all the events that are correlated to this identifier. So let's say we start with order 1. So we're going to add these events, E1, E18, E27, E28, because they have the value 01 in the order attribute. Okay, that's easy. And now we dive deeper into the data and add more events that are related to order 01. And related would be, for example, here, X1, X2, Y1, because they're mentioned in this event E27, so they're related. So I know X1, X2, Y1, they're related to O1. So I'm going to add all events that refer to X1, X2, Y1 also to this case, right? So this would be then these events. I'm leaving out the ones that only talk about X3 and Y2 because they're not related to O1. These ones. And I can keep on doing this, right? So until I add all these events. And then I copy this to a new log where I generate a new synthetic case identifier O1, right? Because so they all didn't have O1, but I'm basically materializing, look, you're related to O1. So that's it in a gist. Now I have to do this for O2 as well, for the second order. So this is now the event log that I would extract. Who sees the problem with this log? With duplicated events. So we have, for example, E3 occurs twice, once for O1 and once for O2. I mean, I had to because it's kind of related, right? It's part of the dynamics. So if I'm duplicating events, I'm getting wrong statistics. Yeah. So I have, for example, placing supplier order is 4 times in the data, but it actually only occurred twice. So whenever I try to reason about how often certain activities occurred, or I don't know how much revenue I made in case these events also include amounts, I have to correct for this. I can do this, but I have to. There's another problem that is in here because of this duplication, and that's far worse, that I cannot correct. Who knows what that is, or who can see it? It's easy. What is it? It's too long ago. So the problem is here I see an event receive supplier order followed by an event update supplier order. So there's 2 events following each other that are actually not related because one is for supplier order A and one is for supplier order B. But I don't see that. I'm just looking at O2. So now if I extract this process model, this is going to tell me you first received your products and then you're updated the supplier order. And then the manager goes, what are we doing? And it's not that they did anything wrong. Your analysis approach was wrong. You're doing things in the wrong way. So this is called convergence, where you're connecting, you're creating dependencies between things which are actually unrelated because you're flattening the data from one perspective. So if you push this data into a process discovery algorithm, then you see this coming back, right? So you see, okay, we have this loop around placing supplier orders. We're doing this 4 times. We have the wrong order about updating and receiving supplier orders. Also false performance information. So this one says we have a waiting time to receive a supplier order of 2.2 days, but in reality it's 3 and 5 days. Nothing here makes sense. So that's why we we're researching this artifact-centric, object-centric process mining for a very long time to fix this. So now let me show you how you avoid all this. That's why you're here. What we're going to do, we're going to build a graph. We're going to draw on concepts of knowledge graphs, called this event knowledge graph, because they build it from event data. I'm going to analyze it. The idea is to don't do the mistake of the first one. So we're not going to pick a case identifier. Rather, we take the entity identifiers that are there, and then for each event, we first identify all the related entities, and then order the events per entity. Simple principle. Now you got to work, because I'm letting you do this. So let me go. Here we are. So I just told you the principle, right? So for each event, we have to find out what are the entities related to it. And then we model this as a graph. Let me give you a starting point for building this. I create for each event an event node. Very simple. So I create a node E5, create a node E9. I give this the label event, and I give it all kinds of attributes, all the attributes that you see in the table. I have another event E18, and then I have E29, and I have E30. So these are all event nodes. Now, what are the entities that are related to, let's say, E30? R5 definitely is an entity. We're going to skip over that one. We'll come back to the actor later. So, but it definitely is an entity. So if we leave the actor out, I1. So I'll draw I1 over here, and this is an entity node, right? And I kind of give it also the type. So this is an invoice. What else? P1, definitely. It's another entity. P1. Move this over here. P1 entity node, and I2. And to encode that an event is correlated to an entity, I just draw an edge. All right, now I've modeled event E30 correlates to I1, I2, and P1. If my handwriting would be better, you could actually read it. What about E29? What do I have to do to complete this graph for E29? Just draw an edge, indeed, to P1. So I can do the same thing for E18, right? I draw an edge to I1. There's also O1 for E18, right? So it's also over here. And E9 is correlated to I2. And E5 is also correlated to I2 and also to O2. So that's the structure. Events that are correlated to entities. Now we add behavior dimension. We now look at each entity node, look at all the events that are connected to it, and order them by time. Then we add an edge between two subsequent events. So which edges should I draw? Which edges that order events should I draw based on this principle? So if I look at I1, within the same entity. So I1 correlated to E18 and E30. So I draw an edge. There's nothing else, right? There are no other events. So I draw an edge from E18 to E30. Call this the directly follows edge. You can also label it, it's for entity I1. And notice how it skips over E29, right? Because E29 is not correlated to I1. It's not part of it. So the edge doesn't go there. If I do this for E5, for I2, then I have an edge from E5 to E9 and from E9 to E30. And last one from E29 to E30 is for payment 1. So now I've materialized local traces from the perspective of each entity, right? I don't have a trace for the entire order. I have small local traces for each entity, and they meet here in E30 because that's where the two invoices are paid by payment 1. Apart from that, they're kind of disjoint. They do their own thing. They're local. Okay, so if we do this, so these are all the steps that I just did with you on the slides. Then I get an event knowledge graph. Call it event knowledge graph because it's using the property graph model that's used in knowledge graphs. Well, it's one kind of knowledge graphs. And we're using property graphs because it allows us to model paths, the query path. Well, we have a path here, right, for this invoice too. These are the traces we like so much in process analysis. So here is this event knowledge graph for this data that I made up for this process. What do you see in this graph, in this event knowledge graph? What structures can you see that you find interesting? Yeah. We see something interesting in here. This is massive, so it takes a bit of time. Batching, yes, absolutely right. So we have batching again. Multiple items being put into a shipment. So batching is there. That's good. What else do you see? Yeah. Sorry, this was a bit too loud from there. Can you say it again? Yeah, that's right. Right. So I have as many unpack events over here as I have items because I'm performing this local to each item. Right. So each item individually is unpacked and looked at. An end split. E5, E5, where's E5? No, there. No, you mean E6 here, right? E5. Let me go down to E5. Yeah, so this is an AND split, right? So it's actually the same thing, E5 and E6, right? So you have an event like E5 where O2 goes on, right? The order is being continues to be handled, but then I have this new object in this. I have an AND split in here. Actually, all double incoming outgoing are AND splits. Well, it is an AND split in the sense that we have two concurrent things that kind of meet or split off. My personal opinion is that whenever we do model parallelism in BPMN, something like this is behind it. You don't do things in parallel unless you're kind of splitting up the process into two things. Whether that's physical objects or information objects doesn't matter, but there is some connection, something spawns off or kind of meets at some point. Yeah, so we see two kinds of AND splits, or kind of, so the AND splits are where things are created, right? So I'm getting a new object in there. Here, this AND split, it's not really creating the items because the items have been there before. They just come into my scope of observation. So if I would have been data from the supplier, shipment company, I would maybe see more what has happened to these items before that. I can do that. I have the data. Well, then there's one very obvious thing that you see is we now can see how the supplier orders and the customer orders are related to each other because we see these items here kind of synchronizing the two. Also, the two supplier orders are completely concurrent, independent. You don't see any edge between them, at least regarding information flow. There's probably much more to see in here. So what I want to get across here with this part is that these structures are different from what we're used to, and it takes time to study them. And I think there's many, many interesting things to observe, patterns to look for, to conceptualize, to make it easier. It's crazy. Okay, so, but it doesn't stop there. We can do something with these graphs. We're good in time. One of the things I want to show you is how to infer more behavior than what we have been extracting from this table, because we really just mapped this table into a graph structure. We want to now infer more. And I want to show you how we can analyze causes for delays, right? Remember, KPI wasn't met. What's the reason for it? So one of the difficult things in working with these multiple objects is that these objects are related. And sometimes there's certain things we don't see if we just trace the objects. We also have to sometimes study the relations between the objects or how the dynamics unfold along the relations. I'm going to show you something here. So we have these payments, right? And we remember you have one payment that clears two invoices that are each related to one order. I'm skipping over a couple of modeling steps, but you can identify this from the data with a bit of domain knowledge. You can model this relation between the payment entity and the order entities by simply adding edges in the graph. That's nice. You can't do this in an event log, but you can do this in this knowledge graph. So we added the relations. Now, in order to study behavior across a relation, we're going to reify the relation. Just like what you do in database theory, if you have an M-to-N relation and you want to store it in the database in second normal form, you reify this into a new table, which becomes a derived entity that records this M-to-N relation. We're doing the same thing here. So we're materializing the relation as a new entity. So we have one entity, O1P1, right, that describes the relation between order 1 and payment 1, and O2P1, order 2, payment 1. And then we can, just like we did before, correlate all the events, to these two derived entities, and we're doing this by union. So anything that was correlated to P1 or to O1 is now also correlated to O1P1. And then we derive, again, the directly follows edges. And these are the paths we get. So we get a path from O1, P1 starting create order until the end of the create order. But then we get this new edge over to the receive payment, clear invoice. That's because that's the combined dynamics of the order and the payment. We do the same with order 2 and the payment. And what this gives us is that we understand that there's, if the relation is meaningful, that there's also temporal dependencies between the shipment and receiving the payment and between clearing invoices and packing shipment. Whether this is meaningful or not depends on domain knowledge. In my example, it is important. So you have to follow me now. So we've inferred this behavior, and you don't need to add all these edges that run in parallel with what's there, right? So we only keep the edges which are really new, so that actually provide additional information. So this is my larger graph that also describes how this payment was, well, depending on the first product being shipped, and then the second shipment depending on the invoice being cleared. So now let's analyze a bit the delays, right? We said before, first order needs 7 days instead of the 6 days. Second order needs 8 days instead of the 6 days. There's all the supplier orders, and there was we can analyze, for example, also the delays in receiving the products, because I mean, if I want to ship my products on time, then I rely on my supplier doing things on time. Here, this took 3 days. This took 5 days, but I had to update my supplier order because I made a mistake. So this is probably at fault for having this delay there. But this is just 5 out of the 8 days. So what else was going on? So let's see whether we can understand why we did not ship within the 8 days. So shipment was at event E32. Well, the only event that occurred before that was E31. Now I have so many edges coming in. So who delayed my event E31? Who's at fault, or what's at fault? How do I think about that? The invoice, why? It's the last event that happened before I could do pack shipment. So, right, so if I look at all the predecessors, I look at how many days or how much time has been passing, this was the one that happened last. So if it wasn't for this, I could have maybe been packing everything already 2 days earlier, right? Because that's when I had all the products already. So, but this edge says there's maybe a dependency. Okay, so this was 3 hours earlier. So now I can continue playing this game, right? So now look at who delayed E30. Who delayed E30? Received payment, E29, right? So this is after the payment was received, we cleared the invoice, and then things went on, right? So it's just 15 minutes. Okay, so we keep doing that, right? We're looking at the edge with the shortest time delay of an incoming edge. So this is the path that we travel through to the shortest edges. Now we meet E7 again. Well, maybe there's something more to explore about E7. We're going to do that in a moment. Yeah, but this gives you a completely different idea of how to analyze dependencies and such complex processes through the graph. Okay, take a short break just to. This is also a process. Tunnel construction. Yeah. It's actually even louder if you're in there. So I was my mom is a highway engineer, so she took me to a to the tunnel construction site. We could walk through it. This is a very different process from the things we typically study. This is a single case, right? This is a single case. It's very complicated to kind of grind through the materials, and it's the rock here is very soft, so you actually can't really drill in there or use explosives to move forward. So soft that what they have to do is they have to go in with this truck and they have to pour concrete in here, then get in irons to stabilize the material behind it, let it dry, and that dried material, then they dig out again. And they could do this in the top part and the bottom part. So first they harden the top part, let it harden, then harden the bottom part, dig out the hardened top part, then kind of moved in a meter, do it again. So you can't describe that in a BPMN diagram. You can forget about it. What you have to think about is What are the tools people are using? When are they doing certain things in this space-time context there in this tunnel? And then you think of, okay, who is using which tool at which spot in this thing? And we're actually going to do this now also for this process that we just looked at to understand what was wrong with E7. So if we look at the data, then we didn't look at the actor perspective yet, right? So I left this out, and I designed my example in a very nice way that now the actor perspective is going to give us an interesting additional dimension. So let me switch to the whiteboard again. So we have our graph here, and I want to add, wow. I want to add actor R1 because R1 is involved in this event E7 that kind of was showing up a bit as it's a problematic event in this entire process. R1 is the actor involved. So I want to add the actor as an entity. So what do I do? Checking whether you remember what we did 20 minutes ago. Entity. Something else. No, I treat just as an entity. It is an entity. And that's why I call them entities and not objects, right? It's not an object, it's an entity. It's a thing in the organization, and some things are passive and some are active, but it's an entity. So I just treat it as an entity, which means, right, I'm going to add an entity node, R1 over here. You don't see this a bit. So the events that are correlated to R1 I already highlighted, right? So I'm going to add my nice edges, E1, E2, E3, and E7 over here. There's the correlation edges. I'm modeling this structure. And then I ordered, yeah. In my data, it's not there, right? You see, but in general, yes, of course. I mean, if you have a washing machine installed and it has to be carried up the stairs, you will have 2 people doing this. So yes, they are. Sticking to this example where it's a single actor, what I do now, I add the directly follows edges, right? So I draw the edge from E1 to E2, from E2 to E3, and from E3 to E7 over here. So I have this new path which jumps across all these different objects. If I do this for all the actors in the data, get this. I see it on my screen, but you don't see it. Haha. I get this. So what do you see? What's in there? What's this? Before the A7, there's no communication between this block, this kind of so you already went straight through the solution, right? Very good, very good. So what you see, right? So R1 has been doing creating the order and placing the supplier order, but only for the first supplier A. They didn't do it for B. R3 placed the supplier order for B, and apparently B wasn't, R3 wasn't aware of how many products to order from B. So R1 then later on stepped in to fix it. So here things went wrong. Absolutely, right? So that's the solution to the puzzle. And now you can see it. That jumps in you. There's other things to see in here to learn how this retailer runs this process. Let it sink in a bit more. Look for patterns. Right. Resources are responsible for different parts of the process. That's no surprise, and you would also be able to see this from a resource activity assignment matrix, right? You see this certain clusters, but you also see it here. But within this, you're responsible for different parts of the process. You see more behaviorally. You see more. That is one of the things, right? So maybe now that I've added edges, the availability of an actor or non-availability of an actor explains why certain things didn't happen, right? So before we just looked at the objects, but well, if you have this one key actor who's the only person who's allowed to do certain things and he's busy over there, then he's the cause of the delay. And you will never see this if you just analyze the delays along your items or objects. Yeah. Yeah. There's something else in here. Brian, do you see it? Yeah. 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 So let me direct you to a bit. Let's look at what R4 is doing. There's two subgraphs that I can identify where R4 is going along object 1 and is doing pack shipment and then ship. And then it moves over to O2 and does again pack shipment and ship. And it's again this a subgraph where the resource walks a couple of events, in this case 2, along an item. So these two subgraphs are the same, isomorphic regarding the labels. So in some sense, this actor is doing batch processing over multiple steps. First pack shipment ship, then on to the next one. He's not doing pack shipment ship. I mean, of course, also the time wouldn't work here, but you see more patterns of this kind. When an actor walks multiple steps over an item. I would call this a task, right? Multiple steps together, it's a task. It's one unit of work that you do to achieve a particular goal, putting the things together and then off to the delivery truck. So here's another one that R2 is doing. Receiving the supplier order and unpacking the items. It's also doing that over here, receiving the supplier order, unpacking the items. But they're interrupted here. They step out, do something else, updating the invoice, and then come back. You probably don't want that. That is an inefficiency. You can see it now. So I'm kind of summarizing what I showed you, right? So adding these paths of the actors across the items, and we can look for these patterns, task execution patterns, where an actor performs multiple consecutive actions on the same object. Or let me add this right away. If you don't have multi-object data, this can even be just your classical case notion, right? So multiple steps in the same case with your classical case identifier. Then it moves on over to the next case. So we have all these different patterns, right? So repeating the same complex stuff, task in different cases. Also here, repeating the same complex task in different cases, but being interrupted and then returning. Doing isolated things, and then Costas already revealed the problem that we have. R1 should have been doing this one to kind of do the consistency, and then we would have avoided this delay. And you can classify these patterns, right? So we're coming back to what Arek asked: can you have multiple actors, right? So if you think of these patterns, then what I've primarily discuss with you is things like this, one actor going over multiple steps along one object. But you can think of this broader, working on multiple objects at the same time, over multiple steps, even interrupting it, coming back, or the actor is doing nothing in between while the object is being worked on elsewhere, and then it comes back. So there's a continuity on the task from the along the actor. The actor is not doing anything in between. Really, it's really working on these n objects, and they're updated here and there, or well, consecutively. So we can identify these patterns. We have no idea what they mean. So this is a big question, right? And there's more patterns out there, because once you kind of start combining these smaller ones into larger ones, then definitely there's interesting things to see. There's many more things I could tell you, but I don't want to overload you too much. But what's nice is you can play with this. So everything I've just showed you, you can apply and try out in the graph database system Neo4j. It's open source, also an enterprise version available that for research purposes you can just download, install on your laptop. Building up a tutorial of how to load this data, and especially the data that I've shown you, into the graph database, right? How to build the event nodes, the entity nodes, directly follows graphs, and so on. And it uses query language Cypher to kind of do this. So you can also query the graph and look for structures and patterns, analyze it. We have a large data set created with kind of all these scripts. So with scripts that can translate CSV files from 5 of the real-life event logs that we typically study over into event knowledge graphs. So that shows that we have a lot of multidimensional data available. We just never looked at it in this way. Now you can. So how does this? As I said, you can query. So here's some cases from the BPR Challenge 17, this loan application process. And it's on one hand, it's a classical process in the sense that you handle one loan application, but inside of it, you have a structure. You have the application document, which is here drawn in dark blue. You have in orange offers, and some cases have a single offer. Some cases have multiple offers. And in light blue are the workflow events that are run by the case management system. And what you see here immediately is that there's very different types of cases, right? So single offer, 2 offers which are created in parallel and then also canceled in parallel. 2 offers created sequentially, first one, and then later on another one, and then they're also canceled. Here I only have ones with 2, but you get up to 5 offers in a case. You can kind of study this. You also see the ping pong between working on the application and the workflow activities that are involved in this. So it gives you a richer structure to analyze and more meaningful analysis. This is the BPI 14 data. This is a beast. This is the one data set that nobody really uses in process mining research, BPM research, and that is because the only so it has 4 tables, 4 event tables, and the only meaningful one is around the incident. So kind of tickets, right? Identify something, couple of steps, and it's very flexible and sort of you don't get really nice process models out of it. There's nothing interesting to see there if you just look at the incidents or the interactions. The interesting part is when you combine all this data, all these 4 tables, because you have configuration items, right? So these are hardware or software components that are supposed to be managed, and they exist, of course, much longer than an incident or an interaction. So the configuration items here you see in blue, and it's a very, very small part of the graph, right? So this is actually one configuration item here, kind of goes on, and then there's lots of events I don't show, and then kind of comes back over here. And you have these many incidents that are happening, and here's also an incident that leads to an interaction with multiple steps. So you see, the interesting perspective is to analyze this from the angle of the configuration item, but the data wasn't shown to you in this way. Now in the graph it is. There's also service components that contain multiple configuration items, right? So then you kind of have a level of hierarchy in there. Then you also have changes, right? Updates, software updates, or hardware updates that are being made that then happen. And some of these changes are working on different configuration items. You see this here. This change is done on this configuration item and on that other configuration item over here. So this. But that's one of the big questions that the process owner back then wanted to have analyzed. And I think now we can, but I didn't have the time to do it. So now you can. Now you can look into this. How can we figure this out? Which changes lead to less incidents or interactions because it actually fixes a problem, or whether there's maybe a change that you thought would fix something but increases the problem. And it could be that you had one configuration item that was problematic. You do a change, and that's applied to all identical configuration items that maybe didn't show the problem. And then that other configuration item that was involved in the change suddenly starts showing more problems than before. So now you can do this. Before this, you can't. Couldn't. Here is the BPI 17 data again. And now I'm showing you again, right? So you remember application documents, offers, and the workflow. And the red edges are the actors going over it. There's interesting things to see here. So this pattern here, a couple of steps executed, then moving on. This is user one, this automated user that kind of performs a couple of automated steps of setting up the application, and then jumps over to the next one, then jumps over to the next one. And you see other actors that kind of pick up on this, create an offer, do a couple of updates on the workflow and the application, and then move on and pick up, work on the next application, work on an offer, create a second offer, finish this, and then move on. And then some other actor takes over. This is like social networks over time. This is what we're looking at very, very deeply at the moment. What are the interesting patterns here? How are actors working? What kind of patterns do they form? Do they always perform these patterns in the same way for the same kind of applications, right? So are applications for a house treated differently than for a car, and so on and so forth? So what I want to get across to you with this is, do not aggregate. Yeah? Do not aggregate all the events that you have into a single trace, because these were the tools that we had. Now we have better tools now, so don't aggregate. Don't have separate traces in this graph that kind of synchronize. Don't aggregate the performance information into a single edge, like in the performance. The performance segment doesn't do this, so you're going to see more. Yeah. Yes. Yes. Yeah. 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 So maybe we're now here in this induction deduction cycle, right? So what I tried to show you is, in the past we've been aggregating too much. So let's look at what's there if we don't. And so how we can look at this differently. And obviously, this is not meaningful to look at from a business angle. So we need to aggregate. That's why we're looking for patterns. We try to make this meaningful. We have to aggregate again. And now there's one thing I didn't show you, but I can tell. This is a graph, right? So if you have a pattern, then you can introduce a note here that says, I'm linking to all these underlying events. So you can materialize this pattern in your graph. You can introduce an abstraction level in the graph, and then you can choose whether you want to analyze your data on this higher level of abstraction, aggregation. But whenever you need to, you can go one level deeper. So you keep the context. And I think this is a powerful mechanism to do. But you're absolutely right. Don't study it at this level, but use this level of detail for inspiration to find new ways of aggregation, more meaningful ways of aggregation. Yeah. Each event relates to multiple entities. It always does, because you at least have the case and the actor working on it. There's always at least two entities. Nothing happens in a vacuum. So acknowledge this, take this with you. Sometimes you have lots of entities in there, which means graphs are better when you want to look at these models. There may be a moment where you say, I don't want it. I want to focus on a single one. Sure, but it's important to keep in mind that there's these multiples, and then you need to go for the graph. Brian. Yeah, yeah.
And it's just, I'm just so thrilled. I'm just delighted to see this because you're going into each of those entities has traits in the past. It's fabric. Really.
Yeah.
Like it's,
Yeah. And this fabric gives you context for the events, for the cases, for the objects, and it can use to study. And just like how Gero yesterday said, look, we only see what we're looking for. This is still true here, right? I mean, we're looking for more, so we're making things richer, but there's lots of things that's not in it. But sometimes the patterns you see there give you an indication there's something else that's behind this, and I now have to go looking for it. So by modeling your data in a different way, you're able to capture more of the qualia of the phenomena you want to study. And that, I hope, I'm convinced, I see this in the discussions with industry partners who present this. It is a more actionable means of communication. It resonates better with the problems they're facing. It's easier to connect certain phenomena to these data structures and this way of thinking. I was talking a lot about the data, not so much about the model. So I want to make that final step to modeling, and this is much harder. This is less developed, but I want to show you a few important points. Maybe you've been wondering, are we done with Petri nets now? Because I started with Petri nets and I said, look, a single case assumption, throw it all out. In fact, what I've showed you is the very understanding of Petri nets by Carl Adam Petri himself. So I had the honor to meet him once, 15 years ago. It was in Berlin, and before we went to dinner, my old supervisor said, go ask Carl Adam to explain Petri nets to you. And that question never occurred to me, but I asked her, so I asked, Adam, can you explain Petri nets to me? And he said, when you talk about Petri nets, when you explain Petri nets to somebody else, you don't start with talking about places and transitions and arcs. You start talking about tokens. A token describes an object in a universe. It can be as small as an atom or as large as this building, if you want. It's a thing. And it moves through space and time. And it will, this token, this object, will only change state, in most cases, leaving quantum theory out, will only change state if it meets another object. Then an event occurs. Two objects meet, then some kind of physical, chemical, human, social, whatever reaction, interaction takes place. That's what events are. That's what transitions describe. So these events emerge from two things meeting in space and time. And you don't have spontaneous state changes. Well, not completely true, but let's be honest, for most of the phenomena we study in organizations, this is true. Well, once you look to manufacturing, then of course there's wear and tear, and then suddenly certain things breaks, then where you wouldn't say that there's somebody actively involved. So sometimes you have this, but in the majority, you don't have spontaneous state changes. So when we're modeling, we're always looking, it's a good thing to keep in mind when you study processes, when you model processes, then whatever you describe is the interaction of at least two things. That's what, if your models look like this, then you're probably on the right way. Then you're more complete than when you have too many spontaneous state changes. If you look at our BPMN diagrams, they all have a single incoming, single outgoing edge, except for the gateways. So that's what we're missing in there, right? So how does this thinking translate to models? Now, I told you this is the thinking of Petrinet. So how can we do this? I want to explain the idea of discovering process models in our example data on these two objects only, right? So object types, orders and supplier orders. And you can do it for the rest, but let's first do the simple one. So this is the data, so this is the events. And the idea is very, very simple. For all event nodes that have the same activity name, right? Create order. I create another node that I call a class node, an event class node, with the same label. So here, create order, also count how many. I have 5 unpack events, so I have one event class node of class unpack with weight 5. Simple. I do this for all my labels, right? That's how we also do typical process discovery, right? Look at all the activity names, one node per activity name. And then we aggregate the directly follows edges that we have in the data, right? So I have an edge from E1 to E18 and from E2 to E5. And I aggregate this to an edge from create order to create invoice. As simple as that. So I do this for all the directly follows edges that I have here. And I get this picture. And I remember for which type of entity this edge describes it, right? So this is an edge describing an order moving from create order to create invoice. This is an edge describing place supplier order to update supplier order. And then I can have activities here that participate in 2 different entities, right? Because I have this event E7. So I have 2 directly follows edges going in. It's different types and then branching. It's again an AND split and join. Here, this is an XOR split, right? So because we're looking at an object can't go both ways. So AND splits and joins are the ones where you have 2 different types going in, going out. So activities can be local to an entity or synchronized to entities. Now, this is what happens if you do this for our example data set. Now, this does get difficult to look at. It takes a bit of time. And I think it's easier to look at it if you take it apart and look at one model per entity type, right? That's what Petri said. You have one object and then it meets with another one. And I describe 2 objects meet by, well, this activity and it's this activity creating invoice, and I have this edge. Because when I have the order, and then from the point of the order I'm creating the invoice, then here there's a create invoice activity happening over here. So these 2 synchronize, they do this together. The model is still large, but at least now I can kind of mentally take it a bit apart. I can look at the individual life cycles of the objects and study how they relate. So this is using directly follows graphs. I can also encode this as a Petrinet, obviously, right? I add a place between these 2 things, and then between any 2 activities. So now I have a Petrinet-based model that does this, still with the same meaning that these 2 synchronize. Let's briefly talk about the kind of addition it takes to Petrinets to do this. What you need to do in terms of Petrinets, you need to make your tokens not black tokens, but tokens that are the IDs, right? So I have an order 1 and an order 2, just like in colored Petrinets, but a very simple color, just the token ID itself. Then one important thing in this model is that at the beginning of the life cycle of each object, this object comes into being, so I'm generating a new ID. So it's called new transition in Petrinet theory. So here, whenever I fire this, generate new IDs. And obviously, this is super simple and doesn't capture all the dynamics that you see here, because if I fire this, I don't know which IDs come, right? If I want to generate Y1, Y2 for the orders, then I need to specify more for this transition to generate new IDs, Y1, Y2, and so on. Now, the synchronization edges, I can only fire this transition if I fire pack shipment here, and I fire in 2 to 3 items the pack shipment transition as well. And then they become a single event. Let me illustrate this a bit better. So I actually have to unpack this mentally and say, okay, actually I have 7 Petrinets here, 2 for the orders and 5 for the items. And X1, X2, X3 already moved to this place that pack shipment is enabled, but Y1, Y2 are not. And suppose I have another rule that I'm not showing here that says I want to synchronize this pack shipment for I1, X1, X2, and Y1. So this is not enabled yet to synchronize because Y1 is not there. But if I fire this transition, now it is. And what happens is firing these transitions kind of leads to one synchronized event, just like as we've seen in the graph before. So the Petrinet theory behind is to do this, but you can. So with this idea, this picture is picture of a hydroelectric dam construction in Brazil. You see all these paths over here, and you can imagine construction workers and machines going around. I think you now have an idea of how you could model this. I mean, sure, it's a lot, but you can. Now you have the things in place to do this. You don't have to use Petrinets, to be honest, right? So instead of having a Petrinet here, this can also be actually, it can be BPM diagram, it can be a declare model, because the only thing that matters here is the synchronization of multiple transitions in one step. For those who still have some brain cycles left, I want to show you one thing that we can actually do with these models rather than just creating them, which kind of reinforces one principle of this multidimensional processing. Arik. Yeah.
Yeah.
So I didn't show this on the slides, but in the book chapter for the process mining summer school, that's also linked in the paper that comes with this tutorial, also show how to add the actors as small Petrinets to your model, right? And they have their own life cycle. And it's very funny if you look at this picture, because the items, they're sequential. They don't have loops, right? So very little loops, whereas the actors are cycles. So it gives the impression of cogwheels moving these items forward. It's a very interesting visual impression this gives. Makes you also kind of visually think about processing in different ways. But you can model actor behavior with their own life cycles. I don't know whether Petrinet is the right thing here, to be honest. I mean, of course, you can if you want to describe the data, but if you want to reason about how, I don't know, you want to help actors perform differently, then probably need different notations. So want to kind of bring all these things together, also bring the performance spectrum back in that we had in the beginning to show you how to solve one problem with this multidimensional thinking. So we're looking again at an airport. So it's a very small part of a baggage handling system. It's a conveyor belt. There's where there's other conveyor belts merging onto this one, right? So a bag's coming here, bag's coming here, and then bags from both belts merge in this place, and they merge down here. But you also see we have the activities have start and end. So this is start, this is one start, this is a completion, again, start, completion. Here we have divers where bags kind of can spread out. So it's a very, very simple. Now, one of the problems that we have in when working with these systems is that we don't have a complete event log over all the different steps and activities that are taking place, but only for some. We're only logging when bags are merged onto the main line or when bags are diverted away. So only the red transitions are actually being logged and the white ones are not logged. And if you now have two bags, one coming here, the blue one coming from this part, and the orange one coming, merging in here, then you have these events recorded, right? We're showing this now to you in the performance spectrum, and these two cross. Now we said these are conveyor belts, it's FIFO, they can't cross. So reality is either this, the blue one came before the orange one, and then I had, in this particular time period, two bags on the belt, or the orange one was actually first and the blue one came later, and then I always just had a load of one bag on the belt. But this matters if I try to estimate performance and kind of identify bottlenecks. Well, how to fix this? Well, how to know which one of these it most likely has been? The idea is to replay this partial log over a model of this baggage handling system, conformance checking, and infer the missing data. Now here you see a lot of things apply what I showed you before. So we have this proclet system. It's a Petrinet. It's a monster. Let's take it apart. The red one is the easy one. That's the process, right? So this is where my items are moving. This is what you would be typically modeling as a BPMN diagram or your workflow model. Then we have single server resources or actors, right? In this case, it's machines, right? So when a bag comes, for example, to a scanner, the scanner starts working, it's busy, it's done, and then it is in idle time, kind of idle and can take in the next. And then you have certain amounts of time it takes to process this and until it's ready to do things. So we're looking here again into the queuing theory, right? So parameters that you know from queuing theory. So this server is working here, we have another server over here, right? And each of them has their own parameters. And between servers, we have queues, FIFO queues. You can also model this as a Petrinet. And again, there's at least a minimum transport time through the queue, or waiting time in the queue until you get from the end of the or start of the queue to leave the queue and being served, right? So the waiting time in the queue. We can model this as a Petrinet. And I want to now replay. And we don't want to replay this over kind of this entire Petrinet. We're going to take it apart. So the idea is the following. We first start replaying the bags over the process part. Because we have alignments. They work beautifully for this. So this gives us these traces. One for the bag 51, one for the bag 50. You see here the red marked events. These are the ones that we had observed, and the other ones are unknown. Right? We inferred them. Right? These are the model moves in the alignment. Over here, you see this in a slightly simpler notation without these places. So these two are independent of each other, right? As we do in classical single-dimensional process thinking. Now, let's bring in the resources. We can also replay the behavior over so the data over the single server resources. So we know because this event was logged, it's a start event of a task. By following this life cycle, there must have been the complete event, and sort of they are together because a single server resource. So this must have been the next event of this resource at that point. Also know this here. So we can create local pairs within this. I don't know in which order these two servings came, but I have partial information what the server did at that moment in time. So I can do this for all the different servers. So I'm gradually adding additional dimensions to my trace that I'm reconstructing. So this is still local to the back. I can do the same for the queue. Wherever things are just local to one object, it happens to the queue. Now the interesting question is, what about between the two backs? This is where I maybe have a handover from first the resource works on one back and then on another one, or the queue. In which order do they come? And we get the order by inferring the timestamps of these unobserved events based on the processing and transport times. So if I try to visualize this, technically we're building a linear program that does the following. So we from an observed event, we know if a bag goes from one step to the next, there's at least the minimum processing and minimum waiting time that have to be observed. So we have an earliest points for where the red bag could have been served by M2 and M4. And I can also trace this backwards, kind of by the last observed events. So I can apply this minimum units. This gives me an earliest and latest moment. And these intervals, they overlap. So I get this red areas or parallelograms that give me kind of a space of uncertainty where the bag could have traveled through. Now we constrain this more by looking at the minimum queue transport times and kind of make the areas tighter. And by this, we observe that here, looking at the minimum queue transport times, the red bag has been before the orange bag. Must have been. It's a consequence of the linear program. Can also be that they overlap and then you live with uncertainty, right? But in this case, the logging is precise enough to infer it back. And we've seen in practical experiments that if you don't get these blockages, right, where things get held up, you can reconstruct with very, very high precision. So it's just when blockages are there, then the uncertainty increases so much that you no longer precisely see which bag entered before another one. Yes. Yeah. 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 Well, I don't know how far this goes, but at least exactly. Yeah, exactly. So what I want to get from this, I have another slide too. Let's wait with that. So also this is implement, right? It's discovery. So it's an aggregation operation in this graph database to discover these models. Vadim implemented a beautiful tool to it's a simulation model of a baggage handling system using this PQR system that I've just showed you, right? So process, queue, resources with a performance spectrum. So you can analyze it from all the different angles, study how things behave from different angles. So where is this all going? Smaller advertisement. So we're working on kind of building this up, right? So I've talked about we're using knowledge graphs and how to model item behavior. Well, you can model more in this graph, right? Different layers of knowledge, different layers of abstraction that you want to put together, and then you get a knowledge graph about the system or the process. And where we want to go to is apply pattern mining, outlier detection, prediction forecasting techniques to enrich this graph, and offer an interface where an operator can query this knowledge graph about the process and tell you, okay, there's a problem about to come up, or I have this problem here. What could be the possible root cause? So to assist in understanding processes in a much, much richer way than what we typically do with just, okay, I have a BPM diagram, I'm annotating in red the edges with the delays. So if you're interested, if you know somebody who might be interested in doing a postdoc, come to me. I will have 2 positions to work on this soon. So to wrap this up, I want you to remember that each entity leaves a trace through space and time. And anything can be an entity. It can be an object, an actor, it can be a relation, it can be a queue. It even can be one of these emergent patterns, right? This blockage. And also treat this as an entity and then work with it. And the data an entity leaves a path of events. And we have shared events when entities interact. Then the model and the aggregates of this data, we model the life cycle of this entity type. Or if you don't go for Petri nets, you go for declare, you model the life cycle. You model the rules that govern how this model behaves. And this can be anything, right? We can have mixed models here, right? So you will have a BPM diagram for one part and declare model for another part. And over here, you just have a simple directly follows graph because that's what you want. And they synchronize on the activities because that's where entities who shared events interact. And the reasoning, this is the crucial part. That's what I wanted to get to across in this last part. You can reason over this by decomposing this complex part into individual paths, reason along the way, and then propagate information from one part to the other. At least is what I know. There's probably more ways you can do with that, right? But at least it's what we have learned. So it has many application areas, right? So call centers, queuing networks, healthcare systems, logistics, warehouses, production systems, ERP systems. And I hope you see how these concepts, well, they resonate with some of the phenomena. It's not complete, but it's more. So this was it. This is what I can tell you about where we are. And I hope it gives you a handle for how to continue. I'll upload these slides to LinkedIn. You can also access it right with the resources. Oh, we've got to change the link to the published book, right? Tutorial and lots of papers to pick up on. So thank you very much. But if you still have questions, I'm happy to hear them.